Today we have Dr. Stephen Brus from Argonne National Laboratory. Steve have his PhD in mechanical engineering or in civil engineering from University of Notre Dame. Following his PhD, he did the postdoc at University of Notre Dame and Los Alamos National Laboratory. He is now a computational scientist at Argonne National Lab's Mathematics and Computer Science Division. He is also a guest scientist at Los Alamos National Lab's Fluid Dynamics and Solid Mechanics group of the Theoretical Division. Today, Steve is going to give us an overview of his early career award project. Steve, please.
Okay, thank you. Thanks for the opportunity to talk to you guys about this project that postdoc Coleman Blakely and I have been working on at Argonne for the last 8 months or so. And this is really focused on coastal urban flooding and how we can kind of bridge the gap between the global drivers of sea level change and variability with the high resolution needed to determine the impact of extreme events on coastal areas. So as I mentioned, there's lots of global drivers of sea level change and variability that require global scale models and coupling to other Earth system components. Things like the large-scale ocean currents, atmospheric drivers, the hydrologic cycle, fluxes of meltwater runoff from ice sheets and basal melting under ice shelves. And these types of processes all determine the regional mean sea level, on top of which extreme event processes like storm surge and wave setup and the astronomical tide all combine to influence flooding in a given coastal area. And so while the global scale modeling necessitates sacrifices in terms of lower resolution, the flooding processes really require a high degree of horizontal resolution to be able to model the propagation of these free surface waves in complex coastal areas. And of course, there's many studies showing that extreme sea levels in the future are going to pose a greater threat to coastal communities. This one in particular shows that the 100-year water level in coastal communities across the globe is projected to increase. And there'll be an increase in the world's 48% in the world's land area that's exposed to a risk of coastal flooding from a 1 in 100-year event by the end of the century. And this also greatly affects the U.S. coastlines, as we can see here. The studies that are used to make these projections often have to make a lot of assumptions due to the different scales involved in flooding and sea level change. And so they lack kind of the high resolution necessary to really resolve coastal inundation. Sometimes they make simplified assumptions about how inundation occurs with sea level. Linear superposition of these factors is a big assumption that neglects the nonlinear interactions between them. And also changes in tides as they evolve with ocean stratification and changes to sea level and ice shelf cavity geometry are difficult to include in some of these projections when they aren't included in a coupled model. And so the advance that is proposed under this project is really to bridge these two scales. And I want to just kind of put the context here in terms of going across the top row here of the current classes of models and options that we have for doing this, and then kind of the advance that we propose. So first of all, we have these barotropic coastal models that are 2D models because they're depth averaged and don't resolve the vertical structure of the velocity. That's a pretty good assumption for long wavelength processes like tidal and storm surge. And because they're 2D, they can have very high horizontal resolution in coastal areas, getting down to the tens to hundreds of meters, really necessary to describe coastal inundation. However, obviously they're neglecting all the thermohaline circulation and the contributions that has on sea level variability. And so for this, we would turn to ocean general circulation models, like impasse ocean. These are typically coarser resolution, but they do describe that baroclinic density-driven flow. They are mode split for efficiency reasons, so the free surface gravity waves, which are fast propagating waves, are evolved at a shorter time step than the three-dimensional density-driven flow. And so this is an important capability that helps us gain efficiency for these types of models. However, if we just resolve these down to coastal scales, the computational expense becomes infeasible. The 3D structure, resolving the 3D structure of the vertical velocity in coastal areas would be very expensive in a global model, and the time step criteria would make this prohibitively expensive in the medium to long term. And so the proposed advance that we've come up with is that we would like to extend the temporal mode splitting that we currently do in impasse ocean, and to make it into a spatial mode splitting as well. So we would have the barotropic mode be solved on a high resolution mesh that would be able to resolve coastal areas and propagate tides and storm surge into coastal floodplains, and while having a connection with the sea level variability due to density-driven flow. And so hopefully this allows us to have more comprehensive assessments of total water level and flooding risks under climate change. And so we'd look to have something like what's on the right, where we'd have two global meshes, one of which is barotropic and one of which is baroclinic, that are two-way coupled. The motivation for this is postdoc on this project, Coleman Blakely, worked on a one-way version of this coupling for his PhD. And so in this case, they took the Navy's HICOM model, which is about 12 kilometers. And it's a baroclinic model. And they depth averaged the baroclinic forcing from that model, and they feed it into the ADCIRC barotropic two-dimensional model that has much higher horizontal resolution in coastal areas. And as you can see at these time level, or these time series stations at different locations, you can see that this coupling really impacts the observational comparison of the water levels themselves. And the big improvement here is the 30-day water level. So the blue line here is just the barotropic model. A lot of those variations are due to atmospheric forcing. The red line, now we're incorporating the density-driven flow, and that's allowing us to get a much better observational match with our model, or with his model. And so this is really the kind of motivation here for making this a two-way model that we can put inside, or a two-way coupling that we can put inside an Earth system model. Coleman's really an expert on how the internal tide generation dissipation on the baroclinic mode is involved in this coupling. Because these internal waves are generated at the tidal frequencies, this dissipation term is often tuned to the tidal frequency for incorporation in barotropic tidal models. When you have this baroclinic coupling, though, your depth average velocities are no longer purely tidal, and you need to do something to filter out the non-tidal contributions in this dissipative term. And so previously, before Coleman's work, this baroclinic coupling had actually degraded the total water level accuracy of this model versus purely barotropic results. But now you can see in the purple here, this is the kind of distribution of errors compared to observations at about 570 different global water level stations. The water levels between the barotropic on the left and the baroclinic coupled model on the right are comparable, if not better. And the huge improvement here, again, is in the representation of these average 30-day water levels. So the first task of 4 under this project is the development of this spatial baroclinic barotropic coupling. So we have the primitive equations that impasse ocean solves. As I mentioned, we already split these into a baroclinic and barotropic component. The barotropic part of the total velocity is the depth average velocity. The baroclinic is the zero vertical mean perturbation about that. And so to get our barotropic equations in blue here, we depth average the primitive equations. And that's where this G term represents the vertical average of all the other terms in the full momentum equation. And then We subtract that off of the full momentum equation to get the Baroclinic momentum equation. And so now, in addition to doing the time averaging that's necessary to do the temporal mode splitting, we also are introducing a remapping operation here, where the Baroclinic forcing is fed into a highly resolved barotropic mesh where these equations are solved, and then there's a feedback of the barotropic sea surface flux that goes back into the Baroclinic mode. And because this is a really tight coupling between these two Baroclinic and barotropic modes in the ocean model, we plan to implement this as a standalone coupling inside of the ocean model instead of going through the coupling hub, as we do to communicate between different model components of E3SM. The second task we have in mind is to be able to enable a representation of the steric water level changes. Right now, we're not able to do that due to the Boost-Nesk approximation used in MPAS Ocean, which means that we conserve volume and not mass. And so we don't get the contribution of expansion and contraction of the water column from density changes. And so turns out there's kind of a parallel between the Boost-Nesk equations and Z coordinates and the non-Boost-Nesk equations and pressure coordinates. If you exchange the roles of sea surface height and bottom pressure and reverse and kind of change how you calculate the hydrostatic pressure. The third task is to integrate this capability within the land river ocean coupling that's been developed under the ICOM project. And so this will allow us to solve for inundation in coastal areas on a unified mesh, where we also connect very naturally into riverine inflows to look at compound flooding. And so the goal here is to be able to have our barotropic mode resolved down to kind of the 100-meter order 100-meter scales in U.S. coastlines, and then use subgrid corrections, which have also been developed under ICOM and recently incorporated into MPAS, to be able to incorporate the effects and adjust for the subgrid contribution of really high resolution bathymetry data. Another part of this task is to integrate the wave modeling capabilities of E3SM and to be able to add wave setup as one of the drivers of coastal sea levels. And finally, the fourth task is to really use this for scientific applications so that we can better quantify the changes in evolution in coastal flooding risks under different future emission scenarios. This NASA sea level change tool is really nice, and I kind of envision this being something that we can create and drive with E3SM generated data. But here they're able to, at different points, determine the likelihood and probability bounds on changes in coastal flooding risk and the seasonality and how those things change. Because extremes are obviously very important, but nuisance flooding, due to kind of day-to-day changes in sea level and tides, are also very impactful as well. So we'd like to be able to quantify both extremes and nuisance flooding. And so all of this is really built to hopefully help with kind of the missing link for coastal applications, coastal flooding applications within E3SM, and really aim at some of these longer term experiments that have been set out in the original long-term science plan for E3SM related to coastal inundation and the interactions between sea level rise and extremes. And we're really looking forward to kind of hopefully having this capability be something that can be useful for a lot of different, obviously the coastal ecosystem projects, ICOM interface, which are concerned with mid-Atlantic and Arctic coastal processes, but also being able to provide higher resolution coastal water levels for things like Matt Hoffman's early career, where he's integrating sea level processes into E3SM. Also, the ability to have more accurate tides within the ocean model can hopefully help with dynamic ice shelf applications under the FANCY project, and then improvements in tidal mixing in addition to the coastal applications for E3SM. And tides are something I just kind of wanted to highlight. In collaboration with ICOM, MPAS now has a barotropic tidal configuration that's competitive with some of the most accurate non-data assimilated tidal models due to a number of different contributions. One of which is really key is these variable resolution meshes that resolve deep ocean topographic gradients, continental shelves, and of course coastlines. This type of localized resolution is really important for getting the dissipation correct for modeling tides. But obviously this mesh would be pretty problematic for baroclinic applications. And so the hope is that by doing this spatial barotropic mode splitting, we're able to use meshes like this for the barotropic component and have much more accurate tides within E3SM as well, which hopefully can have, again, impacts in terms of the estuary and tidal exchanges, ocean mixing, and subshelf tidal circulation. So just kind of quickly going over some of our progress to date. MPAS Ocean has typically only been able to support one mesh. Obviously, we need to support two to make this work. After doing kind of a deep dive into the framework of MPAS, we realized that the main data structure, which is this domain data structure, is a linked list. And so we're able to allocate another domain and kind of link it, and it makes it convenient to carry this around the code in a pretty non-invasive way. And this allows us to support two totally different decompositions and variable arrays for different meshes, kind of in a unified way. And so initializing the model with this, we're able to initialize the model with this setup, which is kind of looping over the domains. And there's some subtleties in terms of how, for example, MPI is initiated and things. But for the most part, this is proving to be a pretty effective and non-intrusive way to support two meshes within MPAS. And so one of these domains would be would support the Baroclinic mesh, and the other one would support the barotropic mesh. Another thing that Coleman's been really involved with is collaborating with Vijay and Julian on the Seahorse project. They've helped us bring MOAB into the MPAS Ocean model, done a lot of heavy lifting there, and we've been using that to start remapping the fields that we need to accomplish this two-way feedback within MPAS Ocean. So this is an example of early on in a SOMA test case spin-up. The SOMA test case is here. It's a double gyre test case that has kind of realistic, semi-realistic coastlines and things. So we've been using this as kind of our playground to start remapping some of these fields within the model. And so this is an example of going from the baroclinic to the barotropic mesh with that baroclinic forcing. The part where we really have to be very careful, and is kind of what we're currently working on, is how we remap the barotropic sea surface flux back to the baroclinic mesh. And that's what allows us to maintain consistency in terms of the sea surface height representation between these two modes. So for the barotropic subcycling, the sea surface height is advanced using this sea surface flux depth average velocity times the water column height. In the temporal mode splitting, this is time averaged. And then, so we need to add a conservative remap of this time averaged barotropic flux from the barotropic mesh to the baroclinic mesh. And obviously that has to be done in a conservative way because we want to enforce that the barotropic thickness flux is equal to the sum of the layer thickness fluxes. And so this total velocity here can be split into the barotropic and baroclinic components, and then that allows us to solve for the depth average velocity that satisfies this condition, so that when we update the layer thicknesses in the baroclinic mode, we hopefully preserve the property that the area average of the sea surface heights within this baroclinic cell on the barotropic mesh is equal to the sum of the layer thicknesses. And so that will allow us to make these modes consistent despite having them on two separate resolutions. This is kind of a tricky problem that we're working on solutions for. Typically, the remapping that we do within E3SM is all cell center based. And so the approach where we would take an edge-based flux quantity and reconstruct it at a cell center and do a conservative remap, and then interpolate that back to the edges of the destination mesh isn't actually conserving the flux that we need. And so we're looking at more detailed ways in collaboration with Vijay and Julian to be able to do line integrals along the Baroclinic mesh and sum up the contributions along that edge from these reconstructed values from the barotropic mesh to have a conservative remapping for these fluxes. So this would be that second feedback going from the barotropic mesh to the baroclinic. And so that's kind of the overview I wanted to give. I'd like to thank Zhijing for the opportunity to do this research. Thank Coleman for all of his contributions, and really look forward to hopefully working with a lot of different groups within EtherSM to help really tackle some exciting science with this type of coastal inundation capability. So, thank you.